he's been kind enough to give us a talk today. And I've heard Amnon speak at Sydney Uni a couple of times, and I'm confident that we're in for a very special treat. So please join me in welcoming Amnon, and thank you very much for coming to us.
Thank you for inviting me. So, I'm going to talk about fairly old mathematics. So let me remind you, one of the first things we learn when we do complex analysis is if you take a contour integral, if you have a closed contour, and you have a complex form, so a form of the form f times dz, then you can...
Sorry to interrupt, but we can't really hear anything at Penrith.
Oh.
There should be a clip-on microphone somewhere.
Okay. Okay, so
is that better? Yeah.
Okay. So
can you boost the mic volume at Parramatta, please?
Boost it.
Sorry?
Just wants the volume to go up.
Oh, okay. Okay, so back to contour integration. You have a closed contour and a differential form f times dz. Then you can form the integral of f dz. And one of the things we learn is the Cauchy integral formula. It's equal to 2 pi I, so some constant, times the sum of the residues. So this form will have poles at certain points. And one of the miracles of the subject is that nothing except the poles matters. And so this integral will be 0 if the function is actually holomorphic inside the domain. And otherwise, if the function has poles, then you sum the residues and multiply that by 2 pi I. So, okay, so we learned this a long time ago. Now, what I want to look at is what this says about the Riemann, a closed Riemann surface. So what happens if instead of doing it on the plane, let's say you do it on the sphere. So you compactify the plane at infinity. Okay, one way to think of it is if you compactify the sphere at infinity, then you have the disk, which I've drawn here, but there's also a disk on the outside, which looks just the same. Holomorphically, they are actually isomorphic. So this integral, this contour integral, is the sum of the residues inside the disk, but, okay, because of the orientation, it's also minus 2 pi I times the sum of the outside residues. So this is the inside residues, and these are the outside residues. So now I count all the residues outside, including at infinity. Another way of saying it is that 2 pi I times the sum of all the residues on the entire Riemann sphere is always 0. If you take a meromorphic function on the Riemann sphere, in fact on any compact Riemann surface, any smooth compact Riemann surface, the sum of the residues has to be 0. So let's look at let's remind ourselves of some consequences. So the first consequence we remind ourselves of is what happens if you take, let's f be a meromorphic function. F is a meromorphic function on any compact surface, on a compact Riemann surface. So one way to get a meromorphic one form is to look at d log. What happened here?
Oh, you probably pushed it.
Okay. Look at d log. So this is in local coordinates f dash dz over f. So it's f dash divided by f times dz. Okay, so we can look at this and integrate it. If f is a meromorphic function, this will also be a meromorphic function. And it has the property that the integral, well, okay, so the sum of the residues of this, d log f, is 0. But what is the sum of the residues of f dashed over f? I mean, if you think about it, this is a reminder. Near every point, you can write f dashed, let's look near the origin. You can write f of z is h of z times z to the n, z to the n. So you can always write it as the sum of as a product of a holomorphic function which doesn't vanish at the origin times z to the n. This just says that it has a 0 of order n, so n is allowed to be negative. So it might have a pole of order n. It has, at the origin, it's meromorphic. So it's z to the n might be positive or negative, times some function which is non-zero at 0. Now the logarithm is additive. So the logarithm of f of z is the logarithm of h of z plus n times the logarithm of z. Now the derivative of the logarithm of h of z is a holomorphic one form near the origin. In the neighborhood of the origin, it's holomorphic. It has no residue. So the residue is only contributed by the z to the n, and the residue of z to the n, well, the derivative, the logarithmic derivative of z to the n is n times the logarithmic derivative of z, and the logarithmic derivative of z is 1 over z. So in other words, the log, yeah, d log of f of z is d log of h of z, which doesn't matter because it has no residue at the origin, plus n times d log of z, which is 1 over z. So in other words, the residue at the origin is exactly n. First of all, it's an integer, and secondly, it's exactly the order of the 0 of the function f at the origin. Now all of these n's have to add to 0. So you learn the classical theorem that if you sum over the compact manifold the order of vanishing of the function f at every point, you must get 0. There have to be as many poles as 0, counted with multiplicity. If you take a meromorphic function on any compact Riemann surface, it has exactly as many zeros as poles. They have to balance out. So for the Riemann sphere, this actually almost tells the whole story. For the Riemann sphere, so if we just look at, remember, the Riemann sphere is very simple. You take C, one-dimensional complex space, the complex line, which we understand. We did complex variable, one complex variable. So you look at C, but you compactify it by adding one point at infinity. This theory is about compact things. So you look at meromorphic functions, so they're allowed to have poles, but they have to extend to infinity. This is the trick. So, well, I mean, over C, we feel we understand things. So, for example, if I give you a bunch of points on the plane, then I can specify the function values of these points. I mean, it's easy. I take a function, I can find a function which vanishes at all but one of these points. So I can find a function that vanishes at exactly one of these points, x minus lambda. If this is lambda 1, this is lambda 2, this is lambda 3, and so on, I can take x minus lambda 1 times x minus lambda 2 times x minus lambda 3, and this way I create actually even a polynomial which vanishes at all of these points except one. I can normalize it to be 1. I can normalize it to be anything. And by taking linear combinations of such polynomials, I can get the function to take any values I want at the finite set of points. There's somehow no restriction. Life is easy. Life is simple on the plane. And and these are actually meromorphic. They continue to infinity. The order of the pole at infinity is finite. And yeah, it's more or less the whole story. So if you delete the point at infinity, you can do anything you want. And then what happens at infinity has to balance out the crimes that you committed in the finite plane. For example, you have to have exactly as many zeros as poles. So if you have too many zeros and not enough poles in the finite plane, you'll have to have a large pole at infinity to balance out. So this theory, okay, so there is a theory there. I mean, you aren't completely free. Things have to balance out. Infinity somehow has to compensate for the crimes that you committed on the finite part of the plane. But life becomes much more interesting when you pass to other Riemann surfaces. So let me do the next case. So I'll remind you about the theory of elliptic functions. So we looked at, the baby example was the sphere. So you take the complex plane, and add 1 point at infinity, and that way you get a sphere. Now we want to look at the torus. So slightly more complicated is the case of the torus. Actually, a lot more complicated is the case of the torus. So we want to look at holomorphic or meromorphic holomorphic functions on the torus aren't very interesting. We want to look at meromorphic functions on the complex torus. Well, so what does this mean? So our complex torus we can think of as, well, we can think of as a thing like this in the complex plane, where you identify this with that and that with that. So you somehow roll it to be a torus. Another way of saying it is we take a lattice. We take two complex numbers, A and B, and we take the quotient of the complex plane by the abelian group generated by A and B. So we take A and B, two complex numbers, we choose them to be linearly independent over R, so they form a lattice, and then they generate an abelian subgroup of C, and we can take the quotient of Z by this abelian subgroup, and what we get is some abelian group. We've taken an abelian group, namely C, and divided by an abelian subgroup. We get an abelian group. But it's also a complex manifold. So it's an abelian group and a complex manifold. As it happens, a complex Riemann surface. And we can wonder about its function theory. So what are the functions on this torus? It's an old subject. 19th century mathematics. What are the functions on this? So what are you looking for? You're looking for functions on the plane which have two periods. They're doubly periodic meromorphic functions. So how do you get such a function? Well, the dumbest thing you could do is you could take one of your favorite functions and make it doubly periodic by averaging, or by summing all the translates. So I happen to like the function 1 over z squared. So we can form the p function. P of z is the sum over all integers, over all pairs of integers, m, n in z, of 1 over z minus ma minus nb all squared. All we do is we take the function 1 over z squared, translate it by a lattice point, and then sum over all the translates. It's certainly a recipe for creating periodic functions. It's going to be doubly periodic. Okay, those of you who are careful with your complex analysis will notice that the sum doesn't converge. So, in order to take care of the convergence, I will do this. 1 over ma plus nb squared. Now it does converge. So all I do is I change each of the summands by constant, so that the result now is decreases fast enough. It decreases like r cubed. Doesn't matter. I take care of the convergence. But all I've done is I've changed this by constant. I mean, up to this stupid thing of worrying about the convergence, I've taken the same function. And this still is doubly periodic. It's the p function. So it's a doubly periodic meromorphic function. you can form its derivative, p dash of z. In fact, you can form it by differentiating term by term. And you get, okay, so if you differentiate term by term, this is a constant, it differentiates away, you get the sum of 2, or actually minus 2, over z minus ma minus mb cubed. And this actually is convergent, there's nothing to worry about. So it is a doubly periodic meromorphic function. And one of the strange mysteries is that you have then got them basically all. So maybe I should try to fit this in here. So there are many theorems about this. So theorem 1 is that they satisfy an algebraic equation. So if you put xy is equal to p of z, p dash z, then they satisfy an equation of the form y squared is equal to 4x cubed plus ax plus b. So there exist constants a and b such that y squared is equal to 4x cubed plus ax plus b. So that's the first thing. So they're not unrelated. They satisfy this differential equation. And the second, and perhaps remarkable fact, is that every meromorphic function on the torus can be written, so every meromorphic function on the torus, if Q is a meromorphic function on the torus, you can write it as a polynomial in X, so a polynomial in P is a bad letter, a polynomial in the P function plus y times another polynomial in X. So you have found all the meromorphic functions on the torus. No, I lied. I better allow myself to take quotients of these. So these are all the meromorphic functions which only have the pole at the origin. And you can get all meromorphic functions by taking quotients of such. So back to residues. So I'll come back to this. This is, yes, this somehow the equation I wrote on the last page, the equation y squared is equal to 4x cubed plus ax plus b. I mean, this somehow is the relation of all of this function theory with algebraic geometry. What you have here is an elliptic curve. It's a curve on the plane. It's a collection of all xy satisfying this equation. And one of the many things I haven't told you is that this actually is a parametrization. So all solutions xy to this equation are of the form p of x, p of z, y, p dash of z. So there exists a lattice. There exists a and b. Remember, the p function depends on the choice of a lattice. You have to choose an a and a b. So they exist. Yeah, I have A and B in this equation. This is
The
terrible.
different A's and B's.
Okay, I'll call them A bar and B bar. They have nothing to do with the A and B that I chose. Well, they have something to do, but they're not the same. Okay, so if I give you A bar and B bar, then you can find an A and a B, and therefore a P function, so that the solutions to this equation are, in fact, parameterized by P of z, P dash of z. So every solution is of the form P of z, P dash of z, and the z is unique up to changing by a lattice point. I mean, P of z and P dash of z are periodic, so you get the same values if you change by a lattice point. But what I'm trying to say is the points of this, the solutions to this equation are in bijection with points on the torus. Yes?
So the P and the P prime are complex value functions.
Yes.
And your X and Y
Are all complex solutions
All
to this
complex.
equation. Everything's over the complex numbers right now.
So they're elliptic curves in the complex plane.
Yes, yes. Sorry, I'm developing the complex theory. There is also a theory of other fields, but the complex theory came first. So the P functions are 19th century stuff. It's old stuff. So there are a number of theorems. I won't get to tell you all of them, but okay, so we're talking about function theory, but it's actually related to solutions to the equation, to this equation. So it's related to solutions to polynomial equation. It's actually, at some level, algebra, not analysis. It's a subject where algebra and analysis cross over. Anyway, we were on the subject of residues. So what do we learn from residue considerations? Well, so we have our little torus. Remember, we started in the complex plane. Here is 0. Here's A, and here's B. Here's A plus B. So we take the quotient of the complex torus, of the complex plane, by the lattice generated by these points A and B. It gives us a torus. And I told you a little bit about meromorphic functions on this torus. Now, one thing we know, so one thing we know from what we've already seen is if F is meromorphic, then it has as many zeros as poles. As many zeros as poles. So this we proved in general for any compact Riemann surface. The number of zeros and the number of poles have to cancel. So if you remember how we proved it, we looked at d log f and formed its contour integral. So we argued that the residues of d log f have to add to 0. That was basically the proof. Now, I want to do something slightly different. I want to look at what do I want to look at? I want to look at z times this. So you can integrate this along the contour. So you can form the contour integral. And the integral along this contour is going to be the sum of the residues inside. So let me not do the details. You can do it. Anyway, the integral, the difference between log f, the point is that f is periodic. So log f, well, f will be the same on this interval as it is on that interval. But log f is not a well-defined function. It's a multi-valued function. If you remember, it has problems. The logarithm of a number is only defined locally. If you analytically continue it, you're not guaranteed that the logarithm on this line will be the same as the logarithm on that line. All you're guaranteed is that they will differ by 2 pi I times an integer. So these don't quite cancel. What you get is 2 pi I times an integer as the difference. So if you take the integral, you get a times 2 pi I times an integer. If you divide by 2 pi I, which you do in this business, then you get an integer times a. And this, so 1 over 2 pi I times these two integrals will give an integer times b. So if you integrate, you get some integer times a, so ma plus nb,
Use the point on the back.
Okay. Okay. So plus nb. On the other hand, you can so this is what you get if you integrate around the rim. And if you sum the residues on the inside, so 1 over 2 pi I times the integral is equal to the sum of the residues. And we computed what the residues are. So the residues are n at every point where so if f is holomorphic, this contributes 0, there's no residue. And if f is meromorphic, then the logarithm is additive. This is just the integer n. Okay? Where n is the order of 0 of f at that point. Anyway, so you get n times a, where a. I keep overusing the letter a. The technology is defeating me.
It's the small button, or you can just press.
Okay. So it's n s si. So the si are the zeros of zeros. Anyway, the formula ends up telling you that, okay, so let's assume that all of the zeros are simple. So the function f is going to have a bunch of zeros here. It will vanish at these points. And what you learn from integrating this is that the points at which it vanishes add to 0 in the group law. They add to a lattice point. The sum is of the form ma plus b, f plus nb. So I assert, okay, so you get, if you take the integral around the contour, you get a lattice point. You get ma plus nb. And what I assert is that the sum on the other side is just precisely the sum of all of these points in the group law. Just the sum of the points. With multiplicity. So if the 0 has order n, then you count the point n times. And if it's a pole, you count it minus n times.
So that n is a different n to the...
Yes, sorry. N dashed. It's just the order of the 0 pole.
Is it an n dash sub I or something like
Sub
that?
I, yes. One for every I. It just counts. It counts correctly how much that 0 occurs. It can be negative, it can be positive, and it can be different for different points. Anyway, the simple way to say it is, if you count with multiplicity, then the zeros and poles add to 0. In the group law. So suddenly you have a very different situation. So you can no longer distribute the zeros at random. You see, in the plane, you're fairly unrestricted. You could put your zeros anywhere you wanted, and then you paid for your crimes at infinity. And infinity could really be any point. So somehow all points were equal. You could do anything you want at all but one point. And then what happened at that one point balances the rest. But here you get some mysterious relationship. It's not, you cannot interpolate any values at any collection of points. You cannot, for example, specify that the function should have zeros here, there, and have poles there. There's a condition. The zeros and poles have to add to 0 in the group law. It's a mystery. I mean, and it has lovely effects. So what does it mean if we think about the geometry? So remember, there's the geometric side. You can consider the solutions to the equation y squared is equal to 4x cubed plus ax plus b. And how do we get meromorphic functions on this? Well, one good, easy way is to take some polynomial in x and y. So, any polynomial you like. A polynomial of the form x squared plus y squared plus 2x plus 3y plus 7. Okay, so this is a polynomial. If you view it, well, it's a meromorphic function. If you consider, I mean, we are now on the compact surface. I'm only writing the affine part of it. But we consider the compactification. So there are points at infinity. Actually, there's exactly one point at infinity. Anyway, you can look at this polynomial. It's a polynomial on the plane, and it extends to a meromorphic function on the entire disk, on the entire torus. And somehow the zeros of this function are precisely the points where this cubic, where this quadratic, this is q, will intersect this cubic. So you have you have a quadratic, you have an ellipse in the plane, an ellipse, a hyperbola, a conic section intersecting a cubic, and what you learn is that the points of intersection have to actually add to 0 in the group law. Well, okay, so the correct statement is that the zeros, if you take the intersection points, then, and consider them as points on this, which is a torus, then in the group law of the torus, they have to add to the same as the sum of the poles. But in this particular case, all the poles are at infinity. There's one point at infinity. So you have 6 points at which this quadratic will intersect the cubic. And the sum of these 6 points has to be equal to 6 times the point at infinity in the group law. I mean, the way we set it up was that the point at infinity was 0. You see, the embedding was by the p function, and the p function has a pole at 0. It was a sum of 1 over z squared made periodic. So the pole was chosen at 0. So it's 0 which gets taken to infinity. So actually, yes, with the way we chose our 0 in this group law, the rule is that the intersection points of these two curves have to add to 0 in the group law of the elliptic curve. Okay, so this doesn't perhaps strike you as very remarkable. I don't know. Maybe it does, maybe it doesn't. But it does have one consequence. It says that if I tell you 5 of the points, then the 6th one is forced on you. You have no choice. It's determined by the fact that it will have to add up in the group law to 0. So you learn this bizarre fact that if you have two quadrics, 2 equations of degree 2, and a cubic. So you have a cubic, so let's call this C for cubic, and we have a Q and a Q dashed, 2 quadrics. Then Q intersect C is 6 points, and Q dashed intersect C is 6 points. If 5 of the points are the same, then the 6th has to be the same too. Magic. I mean, okay, so if you're not convinced yet that this is magic, let's look at the degenerate case. So of course I haven't proved the degenerate case. The only situation in which I proved it is where things are not degenerate. But let's look at the degenerate case, where we allow these quadrics and the cubics to become 2 lines or 3 lines. We could do this. So Well, actually, let's have more fun. Let's do it with a cubic version. So suppose you have, instead of having just cubics and quadrics, you could do a cubic version. So if you have a cubic 1, cubic 2, and cubic 3, by the same reasoning, C1 intersects C2, and C1 intersects C3. Okay, so this is 9 points, that is 9 points. But they have the property that in the group law, these 9 points and those 9 points have to add up to 0. So if 8 of them happen to be the same, then the 9th also has to agree. Right? So, okay. So let's consider the following. Suppose you have a quadric, an ellipse, and suppose we give 6 points on this ellipse. Now there are 2 ways to draw a cubic which passes through these 6 points. Okay, let's do this. So this is cubic 1, passes through these 6 points, and here's cubic 2. Okay, so let me somehow draw them differently. So okay, so we have 2 cubics and a quadric, and which you can also say is we have a hexagon inscribed in a quadric, and we consider the opposite side. We consider, in the hexagon, we consider 3 of the sides as a cubic. Now, take a look, draw these 2 lines. How should I say this? So, the opposite sides of this hexagon meet somewhere. So I get 3 more points of intersection, where the opposite sides meet. Now, I can draw a line through 2 of them, and now I get a quadric and a line. So that's my 3rd cubic. So what do I have produced? Cubic 1 is the union of 3 lines, cubic 2 is the union of 3 lines, and cubic 3 is the quadric and the line. And the way I've arranged it is they meet at 8 points. So there are 8 points at which the intersection of C1 with C2 and the intersection of C1 with C3 is the same. So it follows that the 9th point is also the same. So you learn the remarkable fact that the 3 points on which the opposite sides of this hexagon meet are actually collinear. So this is an old theorem in geometry. These 3 points are collinear.
Which surface are they collinear on?
Sorry?
They're collinear on the plane.
On the plane, yes. It's plane geometry. It's wonderful. Maybe this is too difficult to visualize, so let me do a degenerate case of this. Let the conic become two lines that meet at the points. So we have 6 points in the okay. And now we draw our hexagon. So I'm about to draw a hexagon. Okay? So I connect.
And then if you want colours, you can push that little, see the black circle at the bottom?
Okay? Yes, colors would be good actually. So,
And just choose one of the...
okay, how about red? So, okay, so we go this, and that, and that will be red. Okay? And so these are 3 opposite sides. And now we want blue. So this will be blue. That will be blue. And that will be blue. Okay? So we can think of it as a hexagon. Anyway, this side is opposite to that side, so this is a point of intersection. Maybe I should choose another color for the points of intersection. Yellow. Okay, so 1 point of intersection, 2nd point of intersection, 3rd point of intersection, and the theorem tells us they're all collinear. I didn't draw it very well, but they're all collinear. So it's an example of a hexagon, okay, a strange hexagon, I grant you, a hexagon inscribed in a quadric. And the theorem, this general theorem, tells us that the opposite sides of this hexagon meet in collinear points.
Only if the hexagon's inscribed in one of these shapes, or
Sorry?
and this is just for hexagons that happen to be inscribed in one of these.
Yes, a hexagon inscribed in a conic has this property. Okay. So all of these are theorems in algebraic geometry. And they all come down to results about residues. Okay, so I should be honest. In this talk, I've given the classical complex proofs. By the way, how much more time do I have?
Well, it's up to you. We've got the room until 5, but the talk was supposed to be an hour. But I mean, we can add a little bit more if you.
Okay, I don't have a clock, so you better stop me when.
Well, I don't really want to stop you right now. It's quite fun, so I'll just keep going.
Okay.
It's 4:30, Amnon.
Okay. Okay, so I should try to wind up. Okay, so. Yeah. So, what I've tried to tell you is that this old theorem, this theorem that we learned as undergraduates. Ah, yes, maybe I should go back to. So the theorem we learned as an undergraduate, that if you take a contour integral, so the integral of f of z of f dz is equal to 2 pi I times the sum of the residues. So this old theorem, first of all, has geometric consequences. If you apply it to Riemann surfaces, you learn wonderful things. You prove things which end up telling you about some points being collinear. So quite far removed from what you would think this theorem is about. But there's another side, there's an algebraic version to the theory that works over other fields. I mean, the proofs using contour integration only work over the complex numbers. So to the extent that I've proved anything in this talk, it's all over the complex numbers. But these theorems can be generalized, they work over other fields. And so there's an algebraic version to all of this, and there's even an algebraic version to the notion of taking residues. I probably shouldn't, at this late stage, I probably shouldn't get into the algebraic version. But there is a theory of algebraic residues. It goes back to at least the 60s, late 60s. What do you mean by taking residues in algebra? How do you take the residue? What do you take the residue of? So the recent progress I would like to report is, here is yet another way of looking at this. So this, I'm not sure I will get to explain what this has to do with complex analysis, but suppose K is a field. K a field, and let R is a K algebra. Then you can form the following. You can form R tensor over R tensor over K with R with arm K R. So this doesn't look like differential forms, but it turns out that there is a canonical map. So there is so there's a map from the n forms on so the n forms on R mapping to this. There is some God-given map. There is a map from Hom K of R into K into this. So that map is simple. If I give you a homomorphism from R into K, you can certainly view it as a homomorphism from R into R just by embedding K into R. Okay? Now, let's take this. So let M M is an ideal. M is a maximal ideal. M contained in R is a maximal ideal. With R on M equals K. So suppose we have such a maximal ideal. Then we can look at the submodule here. So I don't know what you call it. The things annihilated by m to the n, by m to some high power. And this gets mapped to the things annihilated by m to some power here. Okay, so theorem 1, this is an isomorphism. Now, theorem next, you have a map from here to K. If I give you a homomorphism from R to K, you can evaluate it at 1. So there's a homomorphism evaluation at 1. And the magic fact is that if you go from here to there to there to there, it turns out that this is just taking residue. So here is a complicated way of describing the taking residues in a totally functorial way. Okay, I should probably stop here. Thanks very much.
Thank you for that wonderful talk. I don't know a lot about algebraic geometry, so it is quite an achievement for you to give a talk that I can more or less follow. Are there any questions?
You went from the sphere to the torus.
Yes.
How about going further?
Yes. So the theory, yes. There are many interesting questions. So, okay, let me. So here is one observation that's general. Okay, so on any compact Riemann surface, you have the following. If I give you a bunch of data, I mean, remember, part of the problem is I give you a bunch of points on the surface, and I say, can you find a function which takes these values? Can you specify the local data? It has a pole at this point with residue. I give you the local expansion. Here, I want the function to locally look like, at this point, I want it to be z to the minus 13 plus 12 z to the minus 10 plus z inverse plus 5 plus z, okay? And then plus higher order terms. I don't care about the higher order terms. I only specify finite. This is what I want the function to begin with, and then you can fill it out any way you want. But up from order, it should have a pole of order 13, and the beginning of its Laurent expansion should look like this. Okay? So I give a finite number of points, and at each of these points I give you locally what I want the function to look like. Can you find the function? So this is a classical problem on any Riemann surface. And the answer is not always. Shouldn't surprise you. There are restrictions. We learned there are restrictions. For example, on the elliptic curve, if you knew that the function vanished on a set of points, I mean, somehow there are restrictions. You cannot, the collection of points at which it vanishes, the collection of points at which it has the same value has to add up to 0. So you have to expect restrictions. Well, one way you get restrictions is if I take any meromorphic form. If I take a meromorphic form omega, and I multiply it by this, and then sum the residues, I have to get 0. Okay, assuming that the function is holomorphic away from the finitely many specified points. So somehow there are obvious restrictions that are given by the Cauchy integral formula. The sum of the residues has to add to 0, which means if I take this and multiply it by something, then the sum of the residues of the product, if the product extends globally, the sum of the residues must be 0. So every omega puts a restriction. So this is true on every Riemann surface. And then there's a theory on which restrictions are linearly independent. So there's an obstruction theory. You cannot be arbitrary.
I have
Yes.
a question. So on the previous slide, you
Yes.
had this connection between the residues and the algebra.
Yes.
So earlier you told us this miracles of planar geometry which
Yes.
arise from the
Yes.
complex functions. So what algebraic miracles are you getting when you have that map through the algebra? What do you get some surprising things?
Yes. Yeah. You certainly get things we don't understand.
Can you go back to the previous slide? The top left-hand corner, if you tap that folder, yeah, that's it. Yeah.
Okay. Yeah, okay, so let's even begin with the slide. So the first thing that's sort of surprising is that
I'm sorry, is that the tensor and the R tensor are up, or just R tensor are up?
R is commutative, so I'm not sure it makes a difference. But I consider this, yes,
Yeah,
R is
okay,
commutative. But the action of R tensor R here is that one R acts on the right and one on the left.
But R is commutative.
R is commutative, yes. R is a commutative Noetherian ring in everything I say.
Right.
So K algebra. K algebra of essentially a finite type and commutative. So, there are several miracles here. The first, for example, is that this is always a finite R module. So, the statement is even in the derived category. If you take the tensor product of this, the derived tensor product, if you take the torsion, the n torsion, tor n of this with that is always a finite R module, and it vanishes except in finitely many degrees. So this is one of the things you
And
learn.
that comes from the
It comes from, for example, from the fact that we happen to know that it's this. Okay, so it's this only when R is essentially smooth over K. But the fact that it's finitely generated, so this, by the way, isn't my theorem. The fact that this is finitely generated is in a relatively recent paper by Avramov, Yenga, Lippmann, and Nayak. So I'm relatively new to this project. But,
so the project is to discover the miracles that are out there by taking this viewpoint.
yes. So this viewpoint is very new. The idea that one can study it locally through what really amounts to partial homology techniques, and taking tensors over the string R tensor R that I think the first paper that noticed anything like this was a 2008 paper by Avramov and Yenga.
Okay, thank you very much again. Any further questions? Right, so unfortunately they haven't quite figured out how to join people to go to dinner via AccessGrid. So I guess I'll hand that over to you guys at Parramatta. And personally, thank you very much again, Amnon, to have gone to the trouble not only to come to Penrith, to Parramatta, but also to give the talk via AccessGrid so that we can join in. So thanks again.
Thank you.
Thanks, Amnon.
Thanks. Thanks, Leanne.
We'll email you guys at the end.
Yeah. Yeah, work out.
Okay.
So it's up to you. I can stay for a drink. I can't stay for dinner because my son's doing his HSC and his trial is started today. But asked me if I could look